Now we can state Green's theorem. First, recall that a curve C is simple if it never crosses itself. So this figure 8, for instance, is not simple. And closed if any parameterization starts and ends at the same point. So here is an example of a simple closed curve. Now, a simple closed curve encloses a region R. So we can unambiguously talk about sort of the inside, or the interior of, or the region enclosed by C. So we also say, sometimes say that C is the boundary of R. And sometimes this is written, I don't think we'll use this notation in this course, but sometimes this is written C equals partial R, although it's, of course, a different kind of partial than partial derivative. Okay, so when we have this curve C, we can traverse it either counterclockwise or clockwise. So this would be traversing it counterclockwise. So we have an intuitive idea of what this means. We can make it a bit more mathy by saying if we're traveling counterclockwise, then the region R, which is the interior, will always be to your left. Whereas if you're traveling it, traversing C clockwise, the region R will always be to your right. This is for a clockwise orientation. So I mention this because when we discuss the integral over C of something, this will change sign if we change the orientation, meaning the direction we traverse C. So, like we defined the integral of something over C in terms of, or we tried to calculate it using a parameterization. And we showed that using different parameterizations of the same curve will give the same value for the integral, except for the sign could change depending on which way this parameterization traverses the curve. So this is just to say that unless specified otherwise, we will always, so our convention is we will always, for any curve, take the counterclockwise orientation unless we explicitly say otherwise. And again, this is a little bit like, I mentioned this before, this is a little bit like in single variable calculus, we integrate from A to B, and if we put a smaller one at the bottom, then we define this to be the negative. So if you integrated from B to A, you'd be going in the opposite direction. Okay, so now let's state Green's theorem. Let's get our hypotheses out of the way first. So C is a piecewise smooth and simple closed curve. So piecewise smooth means like if I had this this is not a smooth curve, but I can break it up into C1, C2, C3, C4, and now integral over C would be integral C1 plus integral C2 plus integral over C3 plus integral over C4. So we can work with sort of mild deviations from smoothness as long as you can break it up into smooth things. Okay, so let's just comment on why we say piecewise smooth. So then this encloses a region R, and F equals mi, maybe I'll write m of xyi plus n of xyj is a vector field. It's defined on an open region containing this R. And we'll also assume that M and N have continuous first partial derivatives. Okay, so now Green's theorem takes two forms. So the first version is what we might call the circulation curl form. And this says if we integrate C over C, F dot unit tangent vector ds, then this is the same as integrating over the region R the k component of the curl and then with respect to area. Then the other form of Green's theorem is the flux divergence form. Says that integral over C f now dot the normal vector ds is the integral over f of the divergence of f dA. So here this one's measuring the counterclockwise circulation, and that's equivalent to this curl integral. And then this one's measuring outward flux, and this is divergence integral. We might also call this one the normal form, and this one the tangential form. Let's write this out more explicitly. So this left-hand side here, so the left-hand side for the circulation curl form is for integrating m dx plus n dy. Then the k component of curl is going to be del n by del x minus del m by del y dx dy. For integrating for outward flux, we'll be integrating m dy minus m dx and then the divergence will be delta m by delta x plus delta n by delta y dx dy. So we sort of, both versions have like one side where m is paired with x and n is paired with y, and then another side where they're swapped. Again, these are equivalent. So in both cases, what we do is we have whatever is paired with dx. We'll now take the del by del y of that. So here we have m dx, and we look at del m by del y. We have n dx. Now we take del n by del y. And similarly, whatever is paired with dy, now we take del by del x of that. And then whichever one was paired with del by or with dx initially, that is the one that gets the negative sign, which in this case, since there's already a negative sign, turns that just into a positive. So since these are the statements of Green's theorem, you don't want to get into the proof of Green's theorem, but you can see the textbook for a proof, at least in some sort of reasonable cases. So instead, let's just go into examples.